Okay. Good morning, everyone. Can you hear me? Okay. I'm Mohammed Al Utaibi. Today, I'm gonna talk about transformer models. Transformer models. Transformer models is the model that has been revolutionized the machine learning field in the last 10 years. And the main goal in transformer is to take one input and segment it into a number of tokens, and then trying to learn the associations between these tokens. So we take one token at a time and then associate it with all the other tokens in that input. And this allows the transformers to study the associations of that input at a very low level of granularity. Unlike the previous methods where basically do not we assume that we do not need to learn these dependencies at a very low level. However, we can learn the global dependencies after transferring the input into a higher level form. For example, in convolution neural networks, we pass the image into a number of polling and convolution layers to convert it into a higher level form or a smaller matrix. And then we can learn how global elements associate with each other in that input. However, at early layers in convolution neural networks, we do not learn how, for example, far elements are associated with each other. So let's take an example here. So if you look at this image from a higher level lens, you'll see an old man with white hair and white beard. However, if you look at it from a lower level lens, you'll see there is a man who's riding a horse and a woman who's sleeping in the bottom. So in neural networks, we basically pass the image into a number of filters of size 3 by 3 or 5 by 5. And in early layers, we will not be able to associate, for example, this part of the image with this part of the image, since the receptive field of the early layers in the convolution neural network is just the size of our filter, which is the 3 by 3 or 5 by 5 pixels. However, in Transformer, we do not do that. We basically segment the image into a number of tokens, and we associate all tokens with each other, no matter how far away from each other. And this gives the transformer the wider receptive field compared to the previous methods. And the main motivation of that is to learn the long range of dependencies and trying to conceptualize larger inputs like larger images and larger text. So, transform model has been invented by Google in 2017, and their paper that's called attention is all you need. And the term attention is the exact process where basically you learn these associations between the tokens. However, the term attention can be misleading because it is different from the attention in humans and other creatures. Because as we will learn later, attention in Transformer is just similarity matching between these tokens. So, attention started as a method for language models. Basically, we have an input in some form, and we wish to transfer or translate this input into a different form using the transformer. And any kind of content generation models will follow this exact architecture. We have encoders that encode our input from the raw form into a computational shared space that the model can understand. And after that, taking that output from the encoder into the decoder, which basically converts the embedding input into the raw output depending on the desired task. So, for example, if the task is translating the French, this French sentence into the English sentence, the French sentence will go through a number of decoders, a number of encoders, and each encoder has exactly one input, which is the output from the previous encoder. And after passing through all the encoders, we go to the decoding phase, which is basically decoding the information that has been learned in the encoding phase. So each encoder has two inputs: the input from the previous decoder and the input from the output of the last encoder. And we will learn the exact process in which how do we associate these two inputs together. So if you take one encoder block and zoom in, you'll see there are two elements. The self-attention elements that is associated with learning the dependencies between the tokens, and then the feed neural networks, which is basically trying to learn the nonlinear associations between the tokens. So, and the self-attention is basically the similarity matching, the linear similarity matching between the tokens. However, we also wish to learn the nonlinear features in that input using the feed-forward neural network. Do you have any questions so far? So if you take the decoder and zoom in, you'll see there is one additional block, which is called the encoder-decoder attention or the cross attention. So in the self-attention, we learn the dependencies between the token from one input. However, the encoder-decoder attention, we learn these dependencies from two different inputs, not just one input. So this allows the model to associate two different inputs together. And this is very useful for multiple applications like multi-modeling. When we have, for example, text and images, and we wish to have or we wish to learn how these two different inputs are associated together. However, in text generation, it's useful to learn how the output from the encoder is associated with the output from the decoder. So if you take one encoder and, for example, you have three tokens, you pass these three tokens into the encoder independently from each other, meaning each encoder will learn how it is associated with the other tokens independently of how other tokens is associated with it. And this is one of the main benefits of Transformer. It has a lot of this parallelism in its architecture that allows it to be processed into multiple processing units. So after going through the self-attention module, the output will go to the feed full network in order to learn the nonlinear features from that input. So what does attention mean in Transformer? We wish to learn in Transformer how each input is associated with other tokens or other inputs. So for example, if you have a well-trained language models that is based on Transformer, and you take the word it, for example, and you see how other inputs are associated with the word it in the grammatical sense. So for example, you see the word animal or word did not is more associated with the word it more than, for example, the word because. That is because in linguistics, we have this association. So the exact process of learning this association starts by taking one token at a time and convert it into three vectors, which are the queries, the keys, and the values. So each token has its own queries, keys, and the values. And basically, the queries ask the question how the other tokens are important to my token. And the answer of that will be found by the keys. The keys answer the question of the query and tells the query how the other tokens is important or not to this token. And so the keys will tell us how the location or where we can find this answer and the value. So the exact value, the exact answer is found by the value. However, the keys are responsible to tell us where to find it in the value token. And one might ask, why not associating the tokens in the raw form? Why transferring the tokens into the query, the values, and the keys? And the answer is of that is, in Transformer, we wish to learn the bidirectional associations between the tokens, not the directional associations, the one directional associations. Meaning, if we have two tokens and we wish to learn how the first token is associated with the second token, we also want to learn how the second token is associated with the first token. So it's not one direction, it's bidirectional. And also another reason is that if we apply the similarity between the raw inputs, the inputs or the token will always be more associated with itself, since if you apply similarity between, for example, two exact vectors, the answer will be always one. And in Transformer, we wish to learn how the token is also associated with other tokens, not with just itself. So the exact formula of the attention is basically the dot product between the query and the key. So the query is associated with one token, while the key is associated with the other token. And then we normalize it by the number of dimension. We apply the softmax in order to sum everything to one. And the output of the softmax is really the weights of how much each token is important to the query. So these weights will be used as filters to the value. So the value is the exact inputs. So we filter our inputs based on what we have learned from based on this association. So this is as for the self-attention. And cross-attention, as we mentioned, we have two different inputs. And in this example, the two different inputs are from the encoder and the decoder. So we have our input from the decoder, and we will wish to associate it with our input from the encoder. So basically, we take the key, the query, and the value from the encoder, from the decoder, and associate it with the key from the encoder. So now let's take an example of the self-attention formula. Now we have two words, and we convert this word into tokens, and then we convert these tokens into the three vectors, the queries, the keys, and the values, and each token has its own vectors. So if we wish to associate the word thinking with the word machine, we take the query of the thinking and apply dot product of the key of the machines. And this is how we associate these two tokens to each other. We take one query from one token and the other key from the other token. And also, we associate the token with itself. So we apply the query from the first token with the key of the first token to associate it with itself. And this the raw output from the dot product is what we call the raw attention. So it basically tells us how these two tokens are associated with each other. And the higher the value of this attention is basically means that they are more associated with each other. And then we normalize it based on the dimension. And then we apply the softmax in order to sum everything to one. So 88.88 and 0.12 they sum to one. And then we basically apply or multiply the weights with the value, which basically tells us or filters our input based on these weights that we have learned. So in real practice, we do not do this sequentially. We do it all at once. So we arrange all our tokens in a very large matrix, and also the keys and the values. And basically, we take our all tokens and multiply it by the weights to convert it into the queries, the keys, and the values. So these are shared weights across all the tokens. Sorry, across all the tokens. So there is no like distinction between different tokens from each other in these weights. And also, it's very common to have multiple heads or multiple self-attention. You do have a question? So basically, in this X is the complete tokens. All the tokens are arranged in the big matrix, and then we multiply. We do the dot product between the tokens and our weights that converted to the queries, the keys, and the values. We do that in a parallel way. Does that answer your question? Um, It's also very common to have multiple heads in the self-attention at the same layer. And it's very analogous to what we have in neural networks, where basically we have multiple neurons at the same layer, and in convolution neural networks, where we have multiple filters at the same layer. So in attention, we have multiple heads in which each we wish to have, or we wish to learn different or diverse features from the different heads. So from each layer, we usually have 8 heads at each layer. So the output from the each attention layer is 8 matrices, and then we combine all the 8 matrices using a shared using the learned weights. So we learn the weights that basically apply the weighted average of these 8 outputs to sum it into one. So to bring it all together, we have all the tokens, and we apply the dot product between the token and the learned weights to convert it into the queries, the keys, and the values. And then we have the outputs from the self-attention modules, and then we weight average all the outputs from the different heads into one output to the next block. So it's not as straightforward as we saw earlier. Sometimes it doesn't make sense how, for example, it is associated with tire, but this is the main benefit of the transformer. Or different heads is to learn diverse information or diverse features from diverse heads. So this is the complete view of one encoder. We take the 2 tokens, we normalize them, we add the positional encoding, which we'll explain later. And then we apply the self-attention. And then in order to prevent the inputs from exploding or maybe vanishing, we normalize the output from the self-attention. And then we apply the feed-forward neural network. And then we go to the next encoder. And the output, as we mentioned, from the encoder goes to every decoder block. So the decoder starts from the output. Each decoder take the input from the previous decoder, and then process it into the self-attention, and then associate the self-attention output with the output from the encoder, and then normalize it, and then going to the next decoder until we reach the linear and the softmax stage, which is after passing all the decoders. And so the positional encoding is important in transformer because, as we mentioned, we process all the tokens together. So in order to give the sense of ordering in the transformer, we add a small bias that basically bias the tokens until inform the tokens how these words are ordered in the input. So basically, usually the tokens or the ordering or the positional encoding start from zero for the first token until the last token. So the encoder phase can happen all at once. So we have the inputs that are arranged in tokens. We pass it to the encoders all at once, and we have our outputs from the encoder. However, in the decoders or the decoding phase, it's sequential because the first input from the decoder is the output from the previous predicted output. Meaning, so for example, here, if we predicted these 4 words, the decoder phase is responsible to predict the next token, which is in this case the end of sentence. And basically, the input of the first decoder is the output from all the predicted words previously. So in order to predict the next token, we need to predict also the previous tokens. So this is how the decoding phase is done. So we have the inputs from the previous encoders, and we associate it with the decoders, with the other inputs from the decoders using the cross attention modules until we predict the next token. Do you have any questions? So in the linear and softmax phase, after passing all the decoders, we basically trying to map what we have learned through the decoding phase with the established vocabulary set in the model. So we have all the vocabularies that we can use in the transformer, and after learned the information or how the input is associated with itself in the decoding phase, we try to predict the next token based on the linear mapping between the information that we have learned and the vocabulary set and defined in the transformer. So after passing through the linear phase, it will give us the probabilities of all the vocabulary sets, and it will pass it to the softmax in order to sum everything to 1. And then we can take the argmax, which is basically the argument of the maximum probability, which is mapped to the higher probable next token. And this happens at different positions. So we do that for the first position, the second position, until we finish, until we reach the end of sentence token, which basically tells the model to stop predicting. So this is the finish of the transformer for language models. If you have any question, maybe you can ask it before moving to the next topic. Okay, for vision models, we have the vision transformer, which is basically the transition from language models to the vision applications. And in the Vision Transformer, they follow the exact same procedure. However, we, instead of dealing with words and each word is associated with one token, we deal with images. So basically, we have one image and we segment it into batches. Each batch is associated with one token. So it starts by projecting these batches into the tokens and then applying the positional encoding that basically give the model the spatial sense of how these batches are organized, and then passing to the transformer the encoder. And after that, we do the MLP head, which is basically classify the content of this image using the CLS token. So so there are multiple variants of the Vision Transformer. The most common one is basically to segment the image into 16 by 16 batches. So each batch has a size of 16 by 16. And if you have an image of size 224 by 224, you will end up by 196 batches, each batch of size 16 by 16. But again, there are multiple variants of Vision Transform. Some of them have smaller size batches, some of them have larger size, and this is kind of the base size for the transformers. So each batch is flattened and passed to the transformer model to learn the self-attention modules. And in theory, so we have one patch that is flattened, and then we apply the dot product between the flattened patch and our weights to convert it into the embedding space. However, in practice, we apply the convolution neural networks in order to convert our patch to the embedding space. And the reason is to apply the convolution network is that it's more efficient. It has the exact output as this big dot product, and we have all the implementation of the convolution networks that we can use from the previous methods. And also, before applying the self-attention, we add to the embedding of the input the positional encodings. So the main reason for adding the positional encoding is basically to give the model the sense of ordering of how each batch is positioned in that image. And for example, if you take one image and apply the mapping between the image and this embedding space, you see that the image is kind of flattened, and there is no sense of how each batch is organized if these batches are processed into the model in all at once, not sequentially. So we calculate the positional similarity, or the positional embeddings of that input and add it to the embedding of that input. And the result will be basically like this. So each batch has some bias of how it is positioned in that image. So the same as the normal transformer, the Vision Transformer, we take one input and convert it into the queries, the keys, and the values. And for each batch, we take the query of that batch. And if we wish to learn how this batch is associated with the other batches, we apply the dot product between the query of that batch and the keys of the other batches. And the result of that will be the score or the attention map. So if we take this attention map and reorganize it, basically it will show us how these, what are the batches that more important, for example, to this exact query. And taking different batches will result in a different attention map. And this is how brute force the transformer model it is, because it's taking all the dependencies and the associations between all the batches with each other. So after passing a number of encoders, we pass it to the MLP head, which is basically trying to learn the non-linearity of the image or the embeddings that we have learned previously. And in Vision Transformer, we do not pass all the tokens to the MLP head. We just take one token that is called the CLS token. And the CLS token is just one additional token that is added to the batches of that image. So basically, it acts as a global anchor of that image, which basically tells how much or the concept or what the image is really about based on the content of that image. And then basically, so this is the main architecture. We have the embedded batches, we normalize it, we apply the multi-head attention, and then we normalize it again, and then we apply the MLP head to classify our input. And there are multiple ways to do the normalization. It depends on the applications. For example, in sequence modeling, since we do not know the size of our batch, we apply the normalization per layer, not per batch. However, in different applications like the vision or the classification, we apply it based on the batch per batch. So these are two different techniques to apply the normalizations. Do you have any questions? So if you do not have any question, I'm gonna ask one question for you. So as we mentioned that the input for a decoder is coming from the previous decoder, right? This is one input. The other input is coming from the other encoder. However, what about the first decoder? What's the input of that first decoder? Because we do not have any previous decoder. Embeddings? Embeddings of what? Yeah, if this is the second decoder or third decoder, but what about the first decoder? No, we do not have decoders in Vision Transformer, so it's just the language models. So language models, we have the encoder decoder. So now let's stick to the language. No. So the second decoder will have the output from the first decoder as an input. So what about the first decoder? It doesn't have any previous decoder. We answered that during the lecture. So the answer depends if we are in training or inferencing. And we answered that in for the inferencing phase. In the inferencing phase, as we mentioned, we basically take all the inputs and passing it all together to the encoder. And after that, we have the output from our encoder. However, in the decoder, it's sequential. We predict the next token. And initially, we predict based on the previous outputs. So the first decoder will have the previous output as the first input, right? So if the previous think, yeah. Yeah. So in this example, the previous predicted output is these four words. So these four words to the first decoder as input, and then the second decoder will take the output from the first decoder as input, and then until it reaches the last decoder. This is for inferencing. We take the yes. Sorry. Okay. There is a token, specialized token that's called the start sentence. That is used when we basically starting everything from zero. And there is also another specialized token which is called end of sentence, which is basically tells the model to stop predicting. Um, so yeah, this is during inferencing. We pass the previous output to the decoder. However, in training, we can do that. We can pass the predicted output, but this will make training very hard, as the randomly initialized model will take very long time to basically predict the correct words, right? So rather than passing the predicted or randomly chosen based on the random weights to the decoder, we pass the ground truth of the output. So basically, we assume that the model has predicted the output correctly. So we pass the ground truth of the output or the previously predicted output to the decoder. And this is called, I think, teacher forcing in the transformer model paper, which will enhance the or speed up the training process. Do you have any question? So in order to prevent, so since we in training we are passing all the sequence or all the ground truth to the decoder, we wish that the training or the model will not cheat based on the ground truth. So since it has also the next token in the ground truth. So what we do is basically to hide the next token from in the ground truth to prevent the model from basically cheating from the ground truth. Do you have any question? It depends on the application. If it is content generation, then as we know from the information theory, we have a very large input, and we learn only the relative information based on the output. So we convert that to the bottleneck stage using the encoder. And then if we wish to transfer it to a different form, we use a decoder to take that back to a different form based on the desired task. So we have this encoder and decoder phase for content generation. However, for classification, we do not need to bring it back to a higher dimensional form, since it's already has been, so since the desired output is just the class of the input. So in that case, we just need to pass it to the encoder.